So now we are going to take 31st problem of crash course at 27 degrees Celsius temperature. The kinetic energy of an ideal gas was E1. We increase the temperature by 300 degrees Celsius. The kinetic energy would be, we know that kinetic energy, they are denoting by E1. E is a function of temperature. It is directly proportional to temperature. It means the ratio of E and T, it should be constant. What do you mean by this? What was initial kinetic energy? What was initial temperature? This ratio should be constant. Means if final kinetic energy is E2, final temperature was T2. E1 upon T1 should be equal to E2 upon T2. If you want to calculate E2, you have to multiply it E1 by T2 by T1. Bus, you have to take care. Temperature should be in Kelvin. What is given? Initial temperature was again 27 degrees centigrade. So we have to add 273. So we will get again 300 Kelvin. What is T2? We increase the temperature by 300. So add 300 in this. It should be 600 Kelvin. So what is E1? E1 was E1. What is T2? It is 600. What was T1? It was 300. So very easily we got the answer. It should be 2 E1 now. Temperature double means kinetic energy double. So we are going with D. If F is the degree of freedom, then Cp upon Cv, you know that what is Cp upon Cv? Cp upon Cv is gamma. And I told you the formula, gamma is 1 plus 2 upon F. So we have to go with B. For nitrogen, Cp minus Cv x. For argon, Cp minus Cv is y. What should be the relation? We know that Cp minus Cv is R. In joules, Cp minus Cv is R. It is Mayer's formula. It is valid for all gases. Either they are monoatomic or they are diatomic or they are polyatomic. We didn't include anything which is the characteristic property of that type of gases. There is a general formula, Mayer's formula, Cp minus Cv should be equal to R. So it means X and Y should be equal. So we are going with A. A gaseous mixture consists of 16 gram of helium and 16 gram of oxygen. The ratio of Cp upon Cv of the mixture is, very important type of problem this is. See, how many moles are there in your mixture? You know that 1 mole helium means 4 gram. So you have in your mixture amount of helium 4 mole, and for oxygen it is 16 gram of helium means 4 mole of helium. And how many moles are there in oxygen? We solved first problem. Molecular weight for oxygen is 32 grams, so half mole. is for oxygen. First we are talking about Cp and Cv for helium. Helium is monoatomic, so Cv was 3/2R and Cp was 5/2R. It is diatomic, so Cv was 5/2R and Cp was 7/2R. We discussed in starting. It means to increase the temperature of 1 mole of gas, to increase the temperature of 1 mole of gas by 1 Kelvin, you need 7/2R. This amount of energy, but we have half mole. So if we want to increase its temperature by 1 Kelvin at constant pressure, we need 7 by half of this, 7/4R. And at constant volume, we need 5/4R amount of energy. For this, for 1 mole, we need 5/2R, and we have 4 mole. So 4 times of this, it means we need 10R energy. At constant volume, 4 times of this, 2 2s and 2 3s, we need 6R. We need 6R. So what we are going to get now, 10R plus 7/4R. So it should be at constant pressure now, we need total energy. We need total energy 10 plus for 4 mole and half mole. It means for 9/2 mole at constant pressure, we need energy 10R plus 7/4R. It means it should be 40 plus 7, 47/4R. And for 9/2 mole mixture at constant volume, we need 6R plus 5/4R. (29R/4). So for 9/2 mole we need this. So for 1 mole means Cp for mixture, we have to divide this by 9/2. So 47/4 divided by 9/2 means multiplied by 2/9. So we are getting 47/18 R. For this, for 1 mole means Cv, again we have to divide by 9/2 means 2/9. So we are getting 29R/18. So for mixture, gamma should be Cp/Cv. Cp/Cv means 18 and R will cancel out, 47/29. So we have to divide 47/29. So what we are getting, we have to divide 47/29. It means simple calculator is allowed. 47 divided by 29. So we are getting 1.62. So we are going with D. So this type of problems are very, very important. How to get gamma for mixture? First calculate how many moles are present in your mixture. So we saw that there were 4 mole of helium and half mole for oxygen. So total number of moles was 4 and half, means 9/2 mole. In your mixture, 2 components were there. One was monoatomic, one was diatomic. They need different energies to raise the temperature by same amount at constant pressure and constant volume. We calculated that amount. By that we were able to calculate gamma for mixture. Take care of this, very important for your competitive exam. It is a problem for rankers. Next, 35th, the ratio Cp upon Cv is gamma for a gas. Its molecular weight is m. Its specific heat capacity at constant pressure is. Specific heat capacity means molar specific heat. It is equal to molar specific heat divided by molecular weight. So, we want to calculate molar specific heat at constant pressure. We know that Cp minus Cv is equals to R. First we are going for molar specific heat. These are molar specific heat, and Cp upon Cv is gamma. In this problem we are focused on constant pressure, so remove Cv. The value of Cv is Cp by gamma, Cp by gamma. So we are putting in this Cp minus Cp by gamma is equals to R. Take Cp common, 1 minus 1 upon gamma means gamma minus 1 upon gamma, it is R. So what we are getting, molar specific heat and constant pressure, we can say gamma R upon gamma minus 1. So now we are capable for this calculation. Cp is R gamma upon gamma minus 1. Divide this by molecular weight. So what we are getting? Gamma R upon gamma minus 1 into m. So we are going with option C. Next, 1 mole of a monoatomic gas is mixed with 3 mole of diatomic gas. What is the molar specific heat of the mixture at constant volume? Again, we have 2 type of gases. Monoatomic. You know that for this Cv is equals to 3/2 R and Cp is equals to 5/2 R. We have calculation in theory part of crash course. What we did there for diatomic? For diatomic it was Cv was 5/2 R and Cp was 7/2 R. Now in our mixture we have 1 mole of monoatomic and 3 moles of diatomic. We want to calculate molar specific heat at constant volume. So we have to focus on this part only. 1 mole gas needs 3 by 2 R energy to increase its temperature by 1 Kelvin. But we have only 1 mole. So for this gas, we need, for this 1 mole at constant volume, how much amount of heat you need? 3 by 2 R. This you have 3 mole at constant volume. You need, for 1 mole to increase its temperature by 1 Kelvin, you need 5 by 2 R. For 3 mole, you need 3 into 5 by 2 R. So total amount you need for 4 mole, 1 mole monoatomic and 3 mole of diatomic. So for 4 mole at constant volume, heat required to increase its temperature by 1 Kelvin is equals to 3 R by 2, and 15 R by 2 means 18 R by 2 means 9 R. For 4 mole 9 R, therefore for 1 mole at constant volume, heat required is 9 R by 4. So it means molar specific heat of mixture at constant volume for 1 mole means molar specific heat is 9 R by 4, a very important type of problem. Next, 37th, 1 kg of a diatomic gas at this pressure, the density of gas was given. What is the energy of the gas due to thermal motion? You know that. What is the formula? What was the formula for P? I told you, very important result, MC bar square. We did in starting of first problem of crash course. P is equals to MC bar square by 3V. What is the energy of the gas due to thermal motion? We want to calculate energy. It is a diatomic gas. It is a diatomic gas. And we did derivation. So for diatomic, it was for monoatomic, 3 by 2 PV. It was for monoatomic what we did. So for diatomic, there are 5 degrees of freedoms. It should be 5 by 2 PV. It should be 5 upon 2 PV. So now volume is not given. So for volume we can write mass is equals to volume into density. For unit kg mass, volume we can calculate by mass upon density. So now everything is given, pressure is given, volume means mass upon density. So now every physical quantity is given in same units, so no need to worry. 5 by 2 pressure is 8 into 10 to the power 4, mass is 1 kg, density is 4 kg per meter cube. So 4 into 2, cancel 8 with 8. So what we are going to get? 5 into 10 to the power 4 joule. So we are going with option B. Take care of this. These formulas are derived for monoatomic gas. For diatomic gas, we have to replace 3 by 5. For polyatomic gas, we have to replace 3 by 6. The internal energy of 1 gram of helium at 100 Kelvin and 1 atmospheric pressure. You know that the internal energy of 1 gram of helium, what is the formula? We know that we calculated for 1 mole of gas. For 1 mole, we have complete derivation. Helium is monoatomic. We did that experiment for monoatomic only, the derivation. For 1 mole energy required was 3 by 2 RT. But we have 1 gram. How many moles are there in 1 gram? 1 gram helium means 1/4, molecular weight is 4, 1/4 mole. So for 1/4 mole, what should be? It should be 3 by 8 R into T. Now we have the value of each and everything. Since decimals they are not using, so I am taking the value of R in a roundup value. 8.31 means you can take 8 because after decibel number is less than 5. So we can drop that. So 3 by 8 R, and temperature is already given in Kelvin. So we get the answer 300 joule. So we are going with C, 300 joule. Next, if 1 mole of a monoatomic gas, gamma is equals to 5 by 3, is mixed with 1 mole of a diatomic gas. Very important type. Again, we want to calculate gamma for mixture. We know that gas has 2 types of specific energies, molar specific heat, Cp and Cv. For monoatomic, Cv is 3 by 2 R. Cp is 5 by 2 R. For diatomic, Cv is 5 by 2 R and it is 7 by 2 R. In your mixture, I am now talking about mixture. In this mixture, we have 1 mole this, 1 mole this, 2 mole mixture we have. So, to increase its temperature by 1 Kelvin and Cp, what we need? 1 mole. For this 1 mole, we need 5 by 2 R. For this 1 mole, we need 7 by 2 R. So total is 5 and 7, 12, 12 by 2, 6 R. And for Cv, for 1 mole monoatomic, energy required is 3 R by 2. And for 1 mole of dia, 5 R by 2. So for 2 mole of mixture, we required energy at constant volume 3R by 2 plus 5R by 2. So what is the total energy? 8R by 2 means 4R. So for mixture, for 1 mole, how much energy is required at constant pressure? Half of this. At constant volume, half of this, 2R. So it is mixture Cp. It is Cp for mixture. It is Cv for mixture. So for mixture, gamma should be Cp by Cv. It means 3R by 2R. So what we are getting? 3 by 2. 3 by 2 means 1.5. So we are going with option B. We are going with option B. Next. The total energy of 1 mole of rigid diatomic gas is diatomic gas and 1 mole gas is. So what is the formula for total energy? We did their derivation. What it was for diatomic? It was 5 upon T RT. For monoatomic, it was 3 upon 2 RT. For polyatomic, it was 6 upon 2 means 3 RT. So we have done that in our derivation. So we are going with 5 upon 2 RT. The heat capacity per mole of water is, it is now one important problem. Water we are considering polyatomic. Why? In water we have one molecule H2O of oxygen and 2 for hydrogen. For polyatomic, the energy required for per mole is 2 mole. We have 2 atoms of H, 1 atom of oxygen. For polyatomic, for 1 atom we need energy 6 by 2 RT means 6 by 2 R. For 1 atom we need energy for polyatomic 6 by 2 R means 3 R, but there are 3 atoms. So total energy required 3 into 3 R. It should be 9 R. So we are going with 9 R. 41st A. 2 mole of oxygen is mixed with 8 mole of helium. One is diatomic, another one is monoatomic. Again we will make table. We are writing mono here, diatomic at this place, and it is 2 plus 8 mixture, but it is 10 mole. 2 plus 8. It is Cp, it is Cv, but not for mixture. For mono, for 1 mole, heat required at constant volume is 3 by 2 R. For Cp, for 1 mole, it is 5 by 2 R. For dia, it is 5 by 2 R. And Cp is 7 by 2 R. What we are getting there now? We have monoatomic gas means helium 8 mole. For 8 mole we need at constant pressure 8 into 5 by 2 R. 2 mole of oxygen. So we need 2 into 7 by 2 R. So total energy required is for 10 mole 4 into 5 20 R plus 7 27 R. For CV 8 moles 8 into 3 by 2 R plus 2 mole of diatomic means oxygen 2 into 5 by 2 R. So total energy required 4 into 3 12 plus 5 17 R. It is 17 R. So now we are going to calculate for mixture CP and CV. CP and CV means energy required for 1 mole. For 10 mole 27 R, so for 1 mole it should be 2.7 R. It is CP for mixture and it is 1.7 R. It is CV. Therefore, gamma for mixture CP by CV means 2.7 divided by 1.7, cancel R with R, means we are not writing R because that is cancelled out. So it means gamma is equals to 27 by 17, 17 ones are 17, 100. It means after point it will 17 6 what we are getting for mixture. No, we don't want to calculate gamma. Simply they were asking for us कि for mixture CV we calculated this, it is 1.7 R. So they want to know only for mixture CV. So it is 1.7 R. So we are going with C option. Next, for a gas molecule with 6 degrees of freedom, the law of equipartition of energy gives the following relation between the molar specific heat and gas constant. We know that at constant volume, energy associated with each degree of freedom, what it was? It was half R. So for 6 degrees of freedom, it should be R by 2 into 6 means 3 R. So we are going with 3 R. We have the derivation. If for a gas R upon CV is 0.67, which type of gas it is? We know that what is CV? CV is 0.67. 0.67 means 2 by 3. Take 3 on that side. So CV is 3 by 2 R. It means it should be monoatomic. It should be monoatomic. If gamma be the ratio of specific heat of a perfect gas, the number of degree of freedom of a molecule of the gas is, we know that what is gamma? Gamma is 1 plus 2 upon F. So 2 upon F is gamma minus 1. So F should be 2 upon gamma minus 1. So we are going with option C. We are going with option C. So in this way we have completed all 45 problems or units of unit 7. In next slides we will start unit 8, last unit from your 11th class syllabus, means waves and oscillations. Thank you.